Here's a problem that we can solve using our three conditions of equilibrium. We have a 100 Newton beam. So the beam itself has weight. And so we'll draw that in right here. Weight equals 100 newtons. It's 8 meters long, and you can see it's already divided up into 8 segments. And that's actually a really useful thing if you're given a problem and you're not given a nice diagram like this, is you can make your own diagram like that to keep track of the distances. Super helpful. There's a 50 kilogram woman standing 1 meter from the end, so she's standing right here. And so she is exerting a force downward, and so that's the woman. Let's call it F woman, and so that's equal to 50 kilograms times 9.8 meters per second squared. There's a rope at each end, so we have a tension, we'll call that T sub L, and a tension here, that's straight up. I know it looks a little crooked, but that's a straight up arrow. And the problem wasn't super specific, but we're going to assume the ropes are going straight upward. So now we look at this problem, and what else do we need to do to analyze it? Well, we need to pick a positive y direction and a positive x direction and a positive direction for torque, which is counterclockwise. And we need to pick an axis of rotation. And so let's go ahead and pick an axis of rotation. Let's go with the left end as our axis of rotation. We just draw a little circle to represent that, and we make a little note that that's our axis of rotation. Now we can go about solving the problem, writing down the equations. We've got summation of forces in the x direction equals, well, there aren't any. All right, so that's not going to be helpful, but we can do a summation of forces in the y direction and set that equal to MAY. And when we're summing forces, our designated axis of rotation completely doesn't matter. Summing forces is just forces. We just look at the forces and we see TL plus TR. Those are both upward, minus the force of the woman, minus the weight, and this thing's not accelerating, static equilibrium, so that's 0. And we know the force of the woman and we know the weight. But we've got 2 unknowns, so we need another equation. And so what we can do is we can also sum the torque, and we can set that, of course, that's equal to I alpha, and it's equilibrium. So we say, all right, well, TL is at the axis of rotation, so that's not creating any torque whatsoever. We've got the woman, her force is 1 meter away, and she's creating negative torque. So we put a negative sign out in front there. Sorry, ugliest negative sign I've ever made. Then we've got the weight, which is also creating negative torque, and so that's weight times 4 meters plus TR times 8 meters equals 0. And we know that the force of the woman is 50 times 9.8, so that's 490 newtons times 1 meter, that's 490 newton meters, minus 100 newtons times 4, that's 400 newton meters, plus 8 meters times TR, or TR times 8, it doesn't matter. And so we get negative 890. We can add 890 to both sides, and I'm just going to continue my work up here. So 8 meters times TR equals 890 Newton meters. And so we can then say TR equals 890 Newton meters divided by 8 meters. So the meters cancel, and we get TR equal to about 100. We go ahead and do that. 890 divided by 8. And that's 111. And a little bit of change, but we'll round it to 3 sig figs. So the tension in the right cable is, or rope, I guess, is 111 newtons. Now we can take that up here and we can say, okay, well, TL plus 111 newtons minus 490 newtons minus 400, or nope, minus 100 newtons. That's the weight. We're just doing forces here. So her weight was 490. The beam's weight was 100, and that's equal to 0. And so we get TL. And so now we just need to add these up. 490 and 100 is 590. And minus 111. So 479 newtons. If it takes you more steps than that, that's fine. But go ahead and work through that. Make sure that I've got this right. So that's one solution to this problem. But we can do this using a different axis of rotation. And let's go ahead and try that. Here we go. We're going to do the same problem. Say, all right, we've got TL, and we've got our 490 newtons and 100 newtons and TR. And now we're going to use a different axis of rotation. So we're still going to use up as positive y and to the right is positive x, not that we have anything in the x. And we're still going to use clockwise for our positive torque. But now let's go with the right end as our axis of rotation. So we can sum the forces in the y direction. And that's exactly the same as before. TL plus TR minus 490 newtons minus 100 newtons equals 0. There's no difference whatsoever. Here I put them in symbolically, but it's still the exact same thing as when we change the axis of rotation. It does not change our forces in any way, shape, or form. However, when we go to sum the torque, that's where you're going to see a difference. All right, so let's do that. So we've got T sub L. T sub L did not create any torque when we did this last time. Here, it's T sub L times 8 meters. It's 8 meters away from the axis of rotation, and if we look at this, we hold it here, and we're pushing upward, it's going to cause a clockwise rotation, which is negative. Then we've got 490 newtons times how far away from our axis of rotation is it? 1, 2, 3, 4, 5, 6, 7 meters away. And it's going to cause a positive torque. We've got our 100 Newton force, and it's 4 meters away. And it's also going to create a positive torque, a counterclockwise torque. And then T sub R is not going to create any torque at all. So we say that's equal to 0, and so now we can do this. We can add this to both sides. We can go ahead and calculate what these are. Let's see, 490 times 7. So we get 3430 Newton meters plus 400 Newton meters equals 8 meters times T sub L. So I added this to both sides, and I did this calculation. So I get 3830 Newton meters equals 8 meters times T sub L. I divide both sides by 8 meters. So I'm just going to go ahead and do that here. And I get 479 T sub L equals 479 Newton. Look at the units here. We've got Newton meters and then divide by meters, so that's newtons, and that makes sense. We're solving for a force, so we better get a units of newtons. And then we put that back up in here. 479 newtons plus TR minus, and I'll go ahead and combine those, minus 590 equals 0. So if we add 590 to both sides and we subtract 479 from both sides, we get T sub r equal to 111 newtons. We go back, 111 newtons and 479. We get the exact same answers. Okay? And these answers do make sense. That it does make sense that T sub r would be a lower tension because the woman's standing over here, and so the rope on the left is supporting more of her weight than the rope on the right is. So as you can see, you get to pick whatever axis of rotation you want. Both of these axes of rotation was fairly easy to work with, and there really wasn't a benefit to picking one over the other. However, in my next video, I'll show you how picking a different axis of rotation will make your job harder.